in section 7.7 now. We're going to talk about fluid force. So we're going to state a few things from physics. We're not going to go into depth on where they came from. We're just going to say that this is how things work. So if we're thinking about an object that is at a depth h in liquid. So an object at a depth h, the pressure exerted on the object, fluid pressure is, I'll call it P, is W times H, where W is the weight density of liquid per unit volume. So when we have something that's underwater, the pressure that the fluid, whatever the fluid is, the pressure that the fluid exerts on this object is just the density of the liquid times the depth that the object is in the liquid. And we're also going to use what's called Pascal's principle. And Pascal's principle says that the pressure is transmitted equally in all directions in this situation where we're under a liquid. The pressure is transmitted equally in all directions. And it depends only on the depth. So there's nothing else that changes the pressure that this liquid exerts. And pressure is force per unit area. So what we're interested in is finding the force on something that's under a liquid. So the force is going to be the pressure times the area, where area is the area of our object, and at depth, and this is at depth h. So our force is just our fluid pressure, which is the weight density of our liquid, times our depth, times the area of the object. So if we have some object that's under some liquid, the force that the liquid exerts on that object is the area of the object times its depth under the water times the weight density of the liquid. And for all of this, we need to remember this h, this depth. We're considering depth to be positive. So if we're considering a positive distance beneath the liquid. So our depth is positive. It can be easy to forget because we're thinking we're under the liquid, so it's easy to think of the depth as negative. So if we have a vertical surface that's underneath some liquid, the pressure is going to vary along that vertical surface because the depth varies. The depth below the surface varies on that vertical surface. So we're interested in finding the force that a fluid exerts on a vertical surface in a liquid And we do that, we're interested in that because the depth varies. So we have to add up all the little forces on each individual piece of area. So that's what we're doing with fluid force. So what we're looking at is if we had like the side of a window in a submarine. What force does the liquid exert on this window in the submarine? We have the side of a tank of water. What force does the liquid exert on the side of the tank of water? So that's the kind of thing that we're interested in here. So let's look at a submerged vertical surface. So we have a vertical surface. And here's we're going to say this is our surface of our liquid. And we have some surface down here. It has some shape. So here's our surface immersed in this liquid. So what I'm going to do is I'm going to put my y-axis here and say this is my y-axis. And we're going to come up with a way of expressing the force on this vertical surface. And here's my x-axis at the surface. I'm going to put my x-axis at the surface of the liquid. And what we're going to do is we're going to divide the surface into thin, horizontal, rectangular strips. What's that? That's our surface. That's our vertical surface that's underneath this liquid. So the liquid extends all around. This is our vertical surface that's in that liquid. So this is the surface of liquid. So we're in a tank. This is in some kind of tank or in a pool or something, and it's underneath the surface. So our distance below the surface of this little thin strip is, I'll put this in blue. This distance is, we'll call it h of y. The depth below the surface of the liquid is some function of y. And I'm going to call the length, we're going to call this dimension the length. The length is some function of y. The thickness of our little strip is delta y. And we're interested in finding the force on this surface from y equals a to y equals b. So to find the force exerted on this surface, we have to sum all the little bits of force on each little individual horizontal strip. So we're saying that the strip delta y is small enough that we can assume that the force is constant over that little strip, and we're going to sum the force on each little strip as we go up from y equals a to y equals b. So this is just like we did for work. We're summing all the little increments of work. We summed all the little increments of work over whatever the thing was that we were looking at. Or for our centroid, for our moments, we found the moment of each little strip and summed those over the entire planar lamina. We're doing the same thing here. We're dividing this into little rectangles. We're summing the force on each little rectangle as we move vertically up the surface. So our little increment of force on this rectangle, I'm going to call it delta F. Delta F sub I is just the force on the ith rectangle. is our weight density of our fluid times our depth times our area. So if we substitute in what we have here, our delta F sub I, our one little increment of force, is going to be our weight density. We're assuming our weight density is constant, it doesn't change, times our depth at this particular Y value, times our area, which is the length times the height of our little rectangle. So our area is going to be L of Y sub I. Our length of our surface can vary. L of X of Y sub I times delta Y. That's our area. And we're going to sum these over the entire surface. And just like we talked about before, we sum these over our surface, take the limit as delta Y approaches 0, as the height of our little rectangles gets smaller and smaller and smaller, and we end up with, it motivates us to define this as an integral. So using this as our motivation, we're going to say that the force F equals our weight density times the integral from A to B of H sub Y, which is the depth as a function of Y, times L sub Y, which is the width as a function of Y, times dy. And we're saying, just so we're clear, H sub Y is the depth, is the positive depth, at the point Y that we're interested in, and L sub Y is the horizontal length of the rectangle, or length of our surface at our particular point. So this is the force exerted by a liquid on a vertical surface submerged in the liquid. And we'll say W is the weight density. So W is the weight density of our liquid. So similar argument to what we used for work, similar argument to what we use for moments and centroids. We're dividing our whatever we're interested in into little rectangles and summing the force of those little rectangles as we move along that surface. So questions on our development here of what we're doing and how we're coming up with our analysis. All right, let's look at a couple of examples of working with fluid pressure. So for our first example, we have an isosceles right triangular plate. Its base is 6 feet. And its height is 3 feet. It's submerged vertically base up. It's 2 feet below the surface of a pool. We want to find the force exerted against one side. So we could think maybe we have a right triangular trough or something, and we're submerging it in a pool. We want to figure out the force that the water exerts on one side of this plate. So what I always suggest with these kinds of problems, if they describe it verbally, draw a little picture. So I'm going to draw a picture of what we have. Here's my isosceles right triangular plate, base up. Here's the surface of the pool. And we need to draw a coordinate system. So I'm going to set my coordinate system right through the center of the plate. So I'm going to say that this is y and this is x. And I like to draw my little representative rectangle in here. So I'm going to draw the representative rectangle. So here's a representative rectangle that we're going to be looking at. So the distance from here to here is 3 feet. And we're 2 feet below the surface of the water. If we call this distance y, what is going to be our expression for the depth? 5 minus y. Because at the bottom we're 5 feet below. So our depth below the surface is going to be 5 minus y. And I like to double check myself. I think, okay, if I'm down here at y equals 0, how far am I below the surface? I plug in 0 here, I'm 5 feet below the surface. So that makes sense. Now we need to, our thickness of our little strip we call dy or delta y. We need to find an expression, we call this x. We need to find an expression for the width of that little strip in terms of y. We're integrating in terms of y. So usually, often in these kinds of problems, that's where the challenge is finding an expression of the width in terms of y. So how are we going to go about doing that? Anybody have an idea? Use the area equation. We could do that. Set up a ratio. I think I like that one a little better. Anybody think even simpler?
What is the relationship between the y and
Right. So there's a direct relationship between the y value and the width. So that's what we're looking for. So let me label some points here. Okay. So the side of the trough is a line, right? Is a segment of a line. So if we call this point 0, 0, what's going to be the coordinates of this point here at the corner? The base is 6 feet wide, it says. So 3, 3, right? So we've gone over 3 feet and we've gone up 3 feet because its height is 3 feet. So we have a point at 0, 0 and a point at 3, 3. So what can we do with those 2 points? Find an equation for the line that represents that this segment is a piece of. So we have 2 points. We can find an equation for the line. And what did you say? Y equals x. It's the slope is 1. So y equals x. So the side of the tank we can say that it's a piece of the line y equals x. So the length or the width, the length function for the strip, so L sub y, is 2 times what we called x here. So L sub y is just 2y. 2x or 2y, they're the same thing. The weight density of water in these kinds of problems, I'll give that to you. So the weight density of water is usually 62.4 pounds per cubic foot. Sometimes there'll be something different, not square foot, cubic foot. 62.4 pounds per cubic foot. So now we can set up our integral. So our force. So our force is going to be the integral from 0 to 3. We're integrating over the vertical surface of 62.4 times our depth below the surface, 5 minus y, times our area. 2y is our length function, and our thickness is dy. And this is not a difficult integral to evaluate. We just have a polynomial, yes.
So in this one, you said y after the same, because if it wasn't, it was y equals x squared or something, but you want it, you have to use y.
Yes, because we're integrating vertically, so we want our width, our length function, we want that expressed in terms of y. Okay? So we integrate this. If we go through the evaluation, it comes out to be 1684.8 pounds. So a couple of things to remember for fluid force problems. Draw a little picture. Set up a coordinate system. Set up your coordinate system. You need to find an expression for the length of your little representative rectangle in terms of y. And remember, your depth is positive in all of these problems. So we could have set our coordinate system going down this way, so y was positive going underneath the water, and then we would have to change the sign to make sure our depth is positive. Our depth is always positive. Yeah, W you would be given. You would be given. I think in the book they might give it in one problem and then they assume that you're using the same thing for every problem. But if it's oil or something, they would give you that W, that weight density.
So when you say what the force on one side, is that what the force is giving us? It's always just one side.
Well, if we looked at the force on the other side, it would be the same, just in the opposite direction.
So just mean that if we use the for only one.
It gives us the force on one side, yes. So if that were like a triangular window in a submarine that was 2 feet below the surface of the water, that would be the force that the water is exerting inward on that window. Yeah, it's a lot of force. It's a lot of force. Liquid exerts a lot of force. Do we want to see another setup of another example? You say no? No more? Okay.
How would you, like, for Webster, that's just how going and setting up
The coordinate system?
the length. Like, this one we found below the line.
Right.
Keeping the line, but for other shapes, how would you know?
It would really depend on the shape. So if they give you a parabolic side, you'd have the equation of the parabola, and that you could get the expression there. If it's a circular plate, then you could I would set the coordinate system so 0, 0 is at the center of the circle, and then you can write the equation of the circle and get y, an expression of y and x in terms of y that way. So it really depends on what the shape is, how you go about doing that.
What are the homework problems?
Homework problems coming up.
Okay, 575.
There you go. On Friday, I want to talk about, talk about an interesting thing that comes out of moments in center of mass, and that's also, we can also relate a similar thing to fluid pressure and fluid force. So on Friday, I want to talk about that really briefly before we talk about trig substitution. It's kind of nice little things that come out of finding the centroid of the shape and how it relates to volume and how it relates to fluid pressure.